Okay, so the first question is, what is an inductor? An inductor is any device that produces a magnetic field when a current is passed through it. And the prototypical example of an inductor would be a long solenoid. Um, a long solenoid, as you remember, produces a uniform magnetic field inside the solenoid and zero magnetic field outside the solenoid. So if you are thinking of a uniform magnetic field, you would imagine that it's a solenoid that produced the uniform magnetic field. This is similar in spirit to how the prototypical example of something that produces a uniform electric field is the parallel plate capacitor, right? So capacitor, the parallel plate capacitor is a device that produces a uniform electric field, and a solenoid is a device that produces a uniform magnetic field, right? Okay, so inductance is defined as the ratio of magnetic total magnetic flux, which is also called the magnetic flux linkage, to the current that produced the magnetic flux. So for example, in a solenoid, the total magnetic flux would be the flux of all n turns of the solenoid. So if each turn has a flux phi b, then the total flux is n times phi b. So if you divide that by the current I, which produces all the magnetic fields, then you get the inductance of the solenoid. The unit of inductance is a Henry, and 1 Henry is clearly 1 Tesla meter square per ampere, because flux is magnetic field times area, so Tesla meter square over amperes. So inductance is just the total flux divided by the current. As an example of that, let's go ahead and calculate the inductance of a solenoid. So inductance is defined as the total flux, which is also called the flux linkage, divided by the current. So we're going to apply this to calculate the inductance per unit length of a long solenoid. So suppose you've got this long solenoid, and it has a length capital L, and let's say that its turn density is little n. So little n is defined as the total number of turns, which is capital N, divided by the length occupied by those turns, so n divided by L. This is all stuff that you've seen before. Okay, so we're going to do total flux over current to get the inductance, right? Let's say the current flowing through the solenoid is I. So the total flux would be N multiplied by the flux through a single turn, right? So that would be the total flux, divided by I would be the inductance, right? Okay, now let's calculate N. So in terms of little n, N is, I should probably, instead of using capital L for length, I should probably use little l for length, and that's probably why I have little l for length in the PowerPoint, just not to, so as to not confuse these two L's. Okay, so I can write capital N as little n times L, and I can write phi b is, so the magnetic field is uniform and perpendicular to the area of each of these turns, and so the flux of through a single turn would be, single coil would be b multiplied by the area of the coil, right? And that divided by I. Now I know what the magnetic field of a solenoid is, so it's going to be NL. Instead of magnetic field of a solenoid, I can write mu 0 Ni. That's the magnetic field of a solenoid. which doesn't have anything inside it, multiplied by A divided by I, and we are done. So this is, the I cancels out, and you get mu 0 n square A times L is what you get. And the question is just asking for L divided by little l, the inductance per unit length, and that's just mu 0 n square A. So this is just a simple illustration of simple application of the formula. Total flux divided by current is the inductance. The next thing that we're going to talk about is self-inductance. Oh, this is a funny pen which keeps changing colors. Wow, that's interesting. All right, okay. I don't like it. Okay, so what is self-inductance? Remember that inductance is total flux divided by current, right? Now, is that flux caused by the current in the device, or is that flux caused by a current in a separate device? So to give you an example, suppose I have just one turn of wire. And suppose I'm sending a current I through this wire, right? And the current is not constant, the current is increasing. Let's say it's increasing. It could be increasing or decreasing. Let's just say it's increasing. So if the current is increasing, then there is a magnetic field felt by this loop, which is caused by the same current that's in the loop, right? So here the magnetic flux is caused by the current in the same device, and that is an example of self-inductance, right? I could have another situation where suppose I have one solenoid like this and another solenoid which is placed facing the first solenoid. Another solenoid like this, and the two solenoids are facing each other, right? Let's say that the first one is connected to a battery, and let's say the current is increasing through the first one, right? So there would be an increasing magnetic field, and the second solenoid, which is connected but it's not connected to any power source or anything, it's just forms a complete circuit. So the second solenoid will feel the changing magnetic field caused by the solenoid in black, right? And so in that case, there will be a flux change in the red solenoid, but that flux change is caused by a current in a separate device, right? So if the current is in the same device where the flux change is happening, then we say that it's self-inductance. And if the current happens to be in a separate device where the flux change is happening, then we say that it's mutual inductance, right? So let's focus on self-inductance for a moment. Okay. So we'll get back to mutual inductance later. Let's get rid of this. So suppose I have this loop and I'm sending, let's ask ourselves what would happen if the current through the loop were to increase, right? So the current through the loop is increasing, let's say, and the current is flowing in the clockwise direction. What is the direction of the magnetic field produced by a current that's flowing clockwise? If you use the right hand rule, curl the fingers of the right hand in the direction in which the current is flowing. Your thumb will point into the page. So that means the magnetic field is going to be into the page. So as far as the loop is concerned, it sees a magnetic field into the page getting stronger, right? So the loop will try to oppose that change. So which way would it like to send its own current? It would like to send its own current in the counterclockwise direction, right? So there will be an induced EMF in the counterclockwise direction. So if current is increasing in the clockwise direction, then induced EMF will be in the counterclockwise direction. So you can see that the induced EMF is opposing the change in the current, the increase in the current, right? Okay, what would happen if the loop already had a steady current? If the current is steady, then obviously nothing happens. There is a magnetic field which is not changing, so there is no flux change or no induced EMF. So suppose the loop was carrying a steady current, right? And then you cut off the current, so you disconnect the circuit. So the current is trying to come back down to zero, so the current is decreasing. Suppose you have a clockwise current that's decreasing. This is just a separate example. You've got a clockwise current that's decreasing. So the loop will see a magnetic field pointed into the board, which is getting weaker. So to counteract that, the loop will try to make its own magnetic field point into the board so that it can help the dying magnetic field. And so the induced EMF in that case will be in the clockwise direction. So if the current is clockwise and decreasing, the induced EMF would be in the clockwise direction. Right? So once again, the induced EMF will oppose the change in the current. Right? This tendency of an inductor to oppose changes in current flowing through it is the self-inductance. So another way of defining self-inductance is the tendency of an inductor to oppose changes in current flowing through it. Changes in current through it. And we saw a very simple example with a single coil of wire, right? Note the difference between inductance and resistance. Resistance is the tendency of a circuit element to oppose current. Inductance is the tendency of a circuit element to oppose changes in the current. So inductance doesn't care if the current is steady or constant. It only kicks in when the current is changing, and the inductance of an element, circuit element, measures how much the circuit element opposes the change in the current. All right? Okay, so now let's go back to our formula for inductance. So inductance of a solenoid is the total flux, so that's N times phi B divided by the current, the total magnetic flux divided by the current, right? Let's multiply both sides by I. So Li is equal to N phi B. And then let's take a derivative of both sides with respect to time. So ddt of Li would just be L times di dt, because L is a constant. And that would be equal to, N is also a constant for a solenoid, so it's N times d phi B dt. Now, does d phi B dt ring a bell? It should. It's just Faraday's law. It's just the flux rule. And it's just the induced EMF, right, from the previous chapter. So we'd seen that the flux rule was the induced EMF is equal to minus N d phi B dt, if you put in the minus sign to include Lenz's law. So you get this very important relationship that the EMF induced in an inductor when the current through it changes is equal to minus L di dt, where I just use this relationship. So this quantifies what I just said a moment ago, that an inductance measures how much the circuit element opposes any change in the current. So if L is large, then for a given di dt, the induced EMF E would be large, right? So it would be a large opposition to that current. The induced EMF always opposes the current. If L is small, then for a given di dt, rate of change of current, the induced EMF will be small, and so it's not going to oppose that change of current that much.